Okay, so in this video, well, let me put this in the middle. In this video, we're going to be talking about intermolecular forces. So, what is an intermolecular force? Let's write a definition down. So, intermolecular forces are interactions / attractions. I'm going to write that in red. Interactions / attractions between molecules or compounds. If you hear any grumbling in the back, my dog is not happy about being in here. So, anyways, I'm gonna go over something very quickly called polarity, because this plays into what we're going to be talking about. So, polarity. Polarity is the distribution of charge between two atoms in a chemical bond. You will not be expected to memorize these, but I'm going to give you some common ones so it'll make it a little easier for you to calculate. If you just know them off the top of your head, you don't have to. I'll give you a table. Okay, so I'm going to write some common electronegativity values. And remember, electronegativity was, pretty much how likely an atom is to pull an electron towards it in a chemical bond. Electronegativity, sorry, I'm not a good speller. Okay, so electronegativity values are the difference between electronegativity values of two atoms in a chemical bond. Pretty much, we already went over that. That's polarity, but let's make a table real quick. These are some very common ones, and you'll see variations of these depending on where you look, but these are the ones I was taught and should be in the textbook. But really depends on which textbook the school uses. Okay. So we're going to write some very common elements that we will see. Okay. So polarity and how polar a molecule is important in determining what type of intermolecular forces you're going to have. So we're going to write down some values we need to know. We have 0 to 0.4 is nonpolar. 0.5 to 1.9 is polar. And this can vary to 1.7. It just depends on what you're looking at, but this is what I was taught. And then greater than 1.9 is ionic. That means that it was such a big difference that the electron was stripped away. Usually you're going to see this between a metal and a non-metal, more likely than not. All right, so I'm going to do two examples using these values up here. So we have N and H, and we will use C and H. So to do this, we do 3.0 minus 2.1. This comes out to 0.9. And then C and H, you'll have 2.5 minus 2.1. This will be 0.4. So a CH bond is nonpolar. Let me make this black so it's the same. So we'll make the answers red. So this is a polar bond because it's between 0.5 and 1.9. and this is nonpolar. So that's the idea of how you can calculate how polar a molecule is, or if it's nonpolar, like you would just use the electronegativity values. We're gonna do a lot of exercises on this, so don't worry, it's really easy. So now we're gonna start talking about our intermolecular forces. So our first one is called a few different things, but it's called dispersion, or it's called London dispersion, or it's called van der Waals force. Pretty much I'm going to refer to it as dispersion because I don't feel like saying all this. Anyway, so it's present in all atoms and molecules. So essentially what's happening, I'm going to use a really simplistic example. Here's our atom, and then here is our other atom. So electrons aren't stationary. So what's happening is, because the negative forces right here, hang on. It's okay. Okay, so in this video, we're going to be talking about intermolecular forces. So intermolecular forces are interactions / attractions between molecules. Sorry, I cannot talk and write at the same time. I do not know why. Okay, so a very important concept we have to talk about before we get into the types of intermolecular forces is polarity. So polarity is the distribution of charge between two atoms in a chemical bond. So pretty much that means is the charge about even, or is it lopsided? So let's write down the formal definition and I'll explain it. It's really easy. So pretty much you're going to be able to determine this by using electronegativity values. There are some variations depending on where you get the info from, but we're going to use what is available to us on the internet and in your textbook. So I'm going to write down some common ones that will really help you if you just know these and off the top of your head when you're looking up the other ones instead of having to look both up. So let's draw a table. I know this is not the best looking table, but it will do for what we're doing. So we have, I'm going to write carbon, nitrogen, oxygen, fluorine, and hydrogen. So these are the electronegativity values for all of these. So the way to tell if something is polar is we have a range of numbers. So this would be nonpolar. That means that the difference in charge is relatively small or there is none. This is polar, meaning that it could have a pretty decent, gap in charge. And then ionic is when it's just really a large difference and it strips the electron away from the metal. So anyways, I'm going to give you two quick examples. So we have NH and we have CH. So the way you would do this is you would have, for NH, you would have 3 minus 2.1. So this would be the polarity or electronegativity value for that that specific bond. And then CH would be 2.5 minus 2.1. And that would be equal to 0.4. So as you can see, this would be polar for this bond. And this is, I'm going to just write NP, but it's nonpolar. And that's how you determine the electronegativity value. Now, this is important because we're going to be talking about the different types of electronegativity forces. Intermolecular forces. All right, so our first one is dispersion, which has a few different names. And I'm going to write all of them down. We have London dispersion, and we have van der Waals force. Okay, so dispersion is present in all atoms and molecules. Like, without this, nothing would really exist. So, dispersion is a really, really weak intermolecular force. It's not strong. It's very temporary, but it is important. So anyways, I'm going to draw like a quick diagram to kind of explain it. So this is our atom, and then, so I'm going to copy this. I don't know why I didn't do it that way in the first place. All right. So right here we have an electron and an electron. Two negatives don't like being next to each other. If you try to put two negatives from a magnet together, they repel, just like two positives would repel. So what's happening is, because the negative of this particular atom is over here, we have, I always forget how to do this. We're just going to do it like this. Oh wait, no, it's this one. Yeah, there you go. So this is our partial positive symbol. Sorry, I've been doing a lot of calculus, and that was for something else. So what happens is, because the partial positive is over here, the negative's over here, it's going to kick this negative to the other side so it can be next to each other. And this is happening so fast that it's probably happening millions of times a second. Just to give you like a perspective on what's happening. But overall, this happening is super important. So the end result is this. We have our electron, and then over here, our electrons over here. So these can be next to each other, and it induces an intermolecular attraction, even though it's temporary. I'm going to write down. So this is our partial positive. And partial negative, if we have those, which we will. Just not here. Okay, so that's how dispersion works on a very simplified scale. It's not too complicated, but just know that it's present in every molecule. And what this is called is an induced dipole, just before I move on. That means it's got two poles. It's got a positive and negative pole. And temporary. Super temporary. Temporary. All right. So if you need to copy any of this, just pause it. And we're going to move on to the next intermolecular force, because I don't want this video to be too long. So actually, I got one more thing to say about dispersion. Spoke too soon. So dispersion forces depend on size. So the bigger or heavier a substance is, the stronger the dispersion force is. Bigger or heavier a substance is, the stronger the dispersion force is. So size can be used to determine the strength when the only intermolecular force present is dispersion. So just make a note of that. Okay, so to give an example of this, remember dispersion's only going to really happens in everything, but if you have nonpolar molecules, that's the only intermolecular force you're going to have in terms of this class. If you take higher level chems, you'll learn about something else, but we're not going to go over it. I'm going to draw both of these molecules out. So this is propane, and then I'm going to draw out hexane. And I really am not happy with myself that I chose this molecule, because that is a lot of H's to write. Just to prove a point. Anyways, so if the only intermolecular force available or present is dispersion, then size is going to be important for that to determine which one is stronger. So in this case, it would definitely be hexane, because it's a bigger, larger molecule. And that's pretty much it for dispersion forces. Now we're going to go over the second one, which is dipole-dipole. So dipole-dipole is a permanent dipole. And it's due to polar bonding. That would be like, for instance, say we had a seesaw, right? And on this side, I don't know, I put like a crate of potatoes, and over here I put like a huge boulder. They're still sharing the seesaw, but obviously this one is sharing it a little more because it's tipped over to him. That's like a good way of thinking about polar bonds. Now, anyways, so it has to be a covalent bond for this. So I'm going to just highlight the differences. Nonpolar is little difference in electronegativity. Let me move this. Little to no En difference. And polar is significant En difference. Okay, so I'm gonna go over some very some common polar bonds, and then one specific nonpolar bond that, like, if you see it, you shouldn't even think about it. Be like, oh yeah, that's nonpolar. So let's I'm gonna have room for this here. You know what? I'm gonna go to. I think we should have room. So I need 1, 2, 3, 4, 5, 6. Barely gonna have room. I'm gonna just get rid of the fancy brackets. We don't need that. All right. So we have. Just copy these down as I'm writing them. These are all polar. So you should be able to kind of tell which one's the least electronegative, but I'm going to highlight those in red. And then our nonpolar, I'm going to just write here. This one's important. So just make a note of that being nonpolar. So, anyways, sorry to crack my knuckles. Copy that, and then we're going to go to the next page. So I'm going to give you an example of what a dipole is. So C is 2.5, and we have O is 3.5. So their difference is 1. So that's within the range of polar. So I'm going to give you a molecule, formaldehyde, just because it's easy to draw. So your partial positive and your partial negative. So how this force works is, yes, we still have dispersion, but now we have two dipoles that can be, because when I'm drawing this little diagram or example, oh wow, what am I doing? When I'm drawing this, what's happening is the partial negative is lining up with the partial positive. And this is happening like billions or trillions of times inside a solution. And that's how a dipole works to strengthen the intermolecular force. Is the polar bond makes it way stronger because it's a permanent dipole. And it'll make the boiling point a lot higher than if it was a nonpolar bond. I'll give you, the reason I use this is formaldehyde. Let me label that. Formaldehyde, we haven't learned this yet, but per mole, which you'll learn what the mole is next unit. Per mole, you have 30 grams of formaldehyde per mole. Ethane, we'll do over here, is it's nonpolar, because remember CH from the last page. But ethane is also approximately 30 grams a mole. But look at the boiling point difference. And this is where intermolecular forces start to become important. So let me write it over here. So the boiling point for formaldehyde, while it's not high compared to ethane, it is way higher. So that is what's happening with intermolecular forces. As they get stronger, they have an effect on the physical characteristics of the actual molecules. So our next intermolecular force is a very specific type of dipole. So this is very important and is very possible one of the main reasons life exists. So hydrogen bonding. It's a specific type. Sorry about my dog. I guess she doesn't like hydrogen bonding. So it's a specific type of dipole. specific type of dipole. But I'm going to give you an example with water and with ethanol. So hydrogen bonding is a dipole, but it only happens with HN, HO, and in cases of HF, but you're not really going to see that. But these are the main two you're going to see, right? Wow, I don't know what that was. Right here. So let's say we had some ethanol, right? And then over here, we also have some ethanol. And this is a horrible drawing of this, but it's just to kind of show you what hydrogen bonding does. So hydrogen bonding only happens between these. It's not going to happen between a C and an H and an OH. It only happens between OHs and HNs. So this dipole is so powerful that it can alter the physical characteristics. And I'm going to use water as an example here, but this is what hydrogen bonding looks like. So you're going to have, you could have another one over here. And then pretty much like you're going to have trillions or billions of molecules. And they're going to be just, kind of forming a grid with each other. But they're still going to be free flowing and everything, but it's what makes the physical characteristics of these so interesting. So I'm going to use water as an example for how strong this intermolecular force is, and your DNA. Your DNA is hydrogen bonded together. It's not there's parts of it that are covalently bonded, but the two strands are actually linked together by hydrogen bonds. So that's why AT and GC fit together. It's because they have differing types of or differing hydrogen bond locations. I don't remember how to draw the molecule off the top of my head, but the reason, this is like a little sidebar, the reason AT is where the helicase is able to go in and split apart the DNA is due to the fact that it only has 2 hydrogen bonds, where GC has 3. So it's that much stronger. Anyways, so hydrogen bonding is also what gives it that the twist of the helix. So for water, such a simple looking molecule, H2O. So water, remember when I showed you that formaldehyde and ethane, like the boiling points? So they had a 30 gram per mole weight. So water is only 18 grams a mole. So H2O. That means for each mole of water, you will have 18 grams of it. The boiling point of water is 100 degrees Celsius, and that is solely due to hydrogen bonding. So say you had, we'll have an H here, O, H, H, O, H. And this is not the best drawing. I'm just kind of doing this off the top of my head. So pretty much what's happening is it's forming all of these connections. Let's pretend there's one over here. There's another one over here. This is bonding with this one, and it's bonding with this one, because it can make 2 connections each. But this is bonding with something. This is over here, over here. Like, it makes this little network of hydrogen bonds. And while they're not chemically bonded, the attraction is super, super strong. And that's what raises the boiling point of water to 100 degrees Celsius. Pretty much hydrogen bonding is one of the strongest, but it's not technically the strongest. This one's not talked about as much. We're going to move on to the next one. But if you have any questions, we're going to go over all of these in detail. I just wanted to give like a quick overview of this. All right, so number 4, would be an ion dipole. So that means we have ionic compound, and we have a polar bond. Sounds kind of weird, but it'll make sense when I show you this. So say I had potassium chloride, and I have a beaker. You're going to get used to seeing me draw these a lot. So I have a beaker, and I, pour this in. So this will split up to K plus 1 plus Cl negative 1. So in here, I'm going to have ions. So what's going to happen is I have my water, and it's partially positive over here, partially negative, and essentially it's going to look like a hydrogen bond almost, but this is going to work with this and with the water molecules in there. So it makes it a little stronger than a hydrogen bond, but we're not really going to talk about it too much. I might just ask you what it is. Just know it's got an ionic compound and a polar bond. It doesn't have to be water. It could be whatever. But anyways, I'm going to leave this here. I'm going to write a few examples down for you. So, and this is where we're going to finish for intermolecular forces. So we're going to write some compounds down, and we're going to write what we think. We're going to check off what we think it has in terms of intermolecular forces, and be aware, yes, it can have more than one. So just remember, I'm going to give you one answer. Everything has dispersion. So use your notes to do this. Don't just kind of do it from memory unless you think you got it. There will be time for that on your test. Okay, so we have N2, CO, and H3. And I'm going to give you the electronegativity values too. Br2, and then we have KCl plus H2O. There's a few of these. If you get these mad, or if you get these wrong, I'm going to be mad because, you should have just seen these. But anyways, the only ones you should need is Br and Cl. Cl is about 3.16 and Br is 2.96 based off of my tables. So take a few minutes and do this. Pause the video. Okay, so I'm going to go over these. Remember, all of these have dispersion. So N2, N is, what is it? It's 3.0. So 3 minus 3 is 0. That falls within nonpolar. It's only going to have dispersion. CO, C is 2.5. Oxygen is 3.5. It's got 1. There's no H's there, so it can't have hydrogen bonding, but it is polar, so it's going to have a dipole. NH3 is 2.1, and N is, N is 3. So you're going to have about 0.9, definitely polar, and it's got the NH, so it's definitely hydrogen bonding. This, Br2, is just dispersion. And this, if you got this wrong, I'll be mad because I literally just went over it. But anyways, so you have hydrogen bonding, polar molecule, and we have an ionic compound. So you're going to have dipole-dipole, hydrogen bond, and ion dipole. All of those are going to be present in there. And that's pretty much what I'm going to be asking you in regards to these. We're not going to go too in depth, but I'm going to just ask on like a quiz or test if you're able to identify what intermolecular forces it has. Do not worry, we're going to go over this in class a lot because I know it's a lot of information. So if you have any questions, just ask, but I'll see you in the next video.